Okay, how you guys doing? It looks like just going to have a couple of you. I appreciate you guys coming in on the meeting at 6 o'clock. We didn't do it at 2 today. So I'm going to post this, obviously, to YouTube for mostly everybody else's benefit. Can you guys hear me okay? Nicole?
Yep,
And Simon?
I can hear you.
Great, great. So, yeah, those were some pretty wild storms we had earlier. Was anybody here affected by those?
No, my dog just spent the day in the bathtub, so.
Well, I had power flickering and things. I have battery backups on important things, but um, whenever we have big storms that roll through, the effects are multiplied several times over because it affects so many different systems, not just network systems. It affects the road systems and telephone systems and cellular systems and people's personal systems, if they have to go pick up kids from daycare, different things like that. So, and we'll talk more about network security when we get into that section, probably tomorrow. I've graded just about all of exam 1. I've got just a few more to grade and look at. I'm kind of going back and re-looking at some of them to give a fair sliding scale so that I can give an appropriate grade. But for the most part, it looks like a lot of people who thought they did a lot worse didn't do that bad. So we'll see. In fact, I have one student drop the class when they probably, I don't know, maybe didn't need to drop the class. I'm not going to say who, of course, but I've had a couple drops. But if you really feel like you need to drop, send me an email, or better yet, rather than an email, call me at that number, that 409-331-5253, and let's talk about it. Maybe there's some other issues that would make you consider dropping the class, like maybe somebody in your family's contracted COVID-19 and you have to take care of them, change your job situation. But I believe that after exam 2, as long as you guys can get through the subnetting part of exam 2, that's probably going to be the hardest part of exam 2. If you guys can get the subnetting down, and I'm going through and I'm looking at some of the subnetting. I've tried to answer a few questions to point people in the right direction, but a lot of people were able to answer their own questions, I think, mostly because you can submit what you have on what you've been working on the electronic version, and it'll grade it for you, and then you can resubmit it. And so hopefully everybody will do okay on that. But I'll after I have to teach 4397 tonight from 8 to 10 p.m. So hopefully I'll still be alive and be able to keep going over some more of those subnetting assignment questions. And, again, if you're still behind or still haven't turned in the subnetting, even though it was due, it's still not too late. Do it anyway.
Are you gonna provide the answers to the assignment?
What's that?
Are you gonna provide the answer to the assignment?
Well, let's see. Before exam 2?
Yes, so we can have a better idea.
I probably won't. Who's asking? Who's that, Sreya?
Yeah.
I probably won't publicly post the answers. I'll take everybody on a case-by-case basis because, frankly, several of the students are getting it, and they'll make a 98, 99, 100 points on it. But if you're not getting it and you submitted the paper version, or you've made 1 or 2 submissions of the electronic version, and you're not getting it, or you're way off, I'm going to try to get that graded and point out the mistakes that you've made, and I'll put comments on the assignment. Well, this is the mistakes that you made, and then that should help you prevent making those mistakes on exam 2. The version of the subnetting for exam 2 is only going to have 5 entities on it, not 10. It'll be a simpler version where you're not filling out so much space. Excuse me, I'm needing to drink something here. talking on the phone all day. So hopefully, have you? I believe you've turned something in, right, Saraya?
Yeah, I did. I just didn't get any grade back. So I don't know like what.
Oh, you mean on the version 1.0 G? You didn't get a grade back on it, or are you talking about?
I didn't submit the paper version. I did the electronic one, the actuals.
It should have given you a grade back. If it didn't, here's what possibly happened. And I'll look at yours after the class. I won't have a full class today because what we'll do is we'll talk about chapters 9, finish up 8, which is just, there's a couple more slides of that. Talk about chapter 9, which is the wide area network channel, today and tomorrow, and then go over what's going to be on exam 2 for tomorrow, and then I'll make exam 2 available probably tomorrow. And then you'll have until this weekend to take that, overlapping with getting into the third part of the class, which is the network security and the network operations, and what we typically refer to as the security section of the class, the third section of the class, which is, I think it's the most interesting part of the class. It's also the most important these days part of the class because of all of the cyber attacks that have been going on. So let me go ahead and let's finish up on chapter 8. Let me go ahead and pull that up and I'll share my screen. Let me do a little screen switch real quick here, if you don't mind. Give me just a minute. I'm going to plug an external screen on so I can pull it up, see a little bit better. Excuse me. Okay, pretty sure I still have chapter 8 in my downloads folder here. If not, I'll pull it down again. And I'll try to make sure that I hit all the important parts of chapter 8. So, by the way, a couple of people, when you're sharing that draw.io assignment to me, make sure that you're actually sharing the actual draw.io file, not just a PDF or a JPEG or an image of the file. I want to actually be able to edit it. Now, I'm not going to edit your version, like in the case of Nicole's, for example. I'd like to use you as an example. You shared your document with me, which is fine to share it as read-only. What I do is I made a copy of it, and then I could edit it and move things around. Because what I was looking for on the draw.io is I was looking for certain minimal best practice things, like making sure that the lines were connected to waypoints so that when you moved icons around, the lines moved with it. That's kind of one of the major ones that, and that's a fairly simple one. That you've labeled your icons, not just throwing some icons up there, but you've given them some sort of a meaningful label, even if you're just making this stuff up, that you're labeling them and that those labels live with the icons. In other words, if I move the icon around, the label doesn't sit on the screen there. Okay, so, and then what we're going to do, by the way, for the advanced version of that is we're going to add documentation. That's primarily what we do with the draw.io, is we add all that missing stuff that people don't put on the first version. Very few people do. Documentation behind the icon, which specifically describes what that element is, how to access that element, some historical information about that element, and I'll show you more specifically what I mean when we get to that point. Okay. excuse me, we were there already. Okay, I had just started talking about VLANs, and I was trying to describe this, and actually I lose a lot of people with VLANs because there's different ways to look at it. First of all, in order to understand what a VLAN is and how to set one up, you have to understand why we do it, and it's primarily for traffic prioritization, because you have not just different functional groups on a network, but you have different types of traffic, and that's really where it shines. Yes, you can take one physical switch, and if it is a layer 3 switch or it has VLAN capability, you can physically assign ports to different functional groups, as in this very simple example of 8 physical ports here, VLAN 10 and VLAN 20. Or better yet, I prefer that most layer 3 switches, most of the nicer ones, let you actually name these VLANs. So instead of VLAN 10 and VLAN 20, you can name it the engineering VLAN or the finance VLAN and name them based on functional group difference. But the original point of a VLAN was to keep from having to get up and move physical cabling around. And that is probably less of an issue anymore, but we still do that, and I still like to be able to do that. We as network managers don't want to have to get up from our desks and touch anything physically or tell anybody to touch anything physically, because that's where most of the problems occur. 99% of the problems occur at the physical layer. It's not hackers, it's not end users doing the wrong thing or dumb things. It's the physical layer. And that's because there's just too much other physical, environmental, external, what's the word I'm looking for? External influencers on the physical layer. So if I'm moving cables around, it's a possibility that I don't plug a cable into the right port. I don't plug it in all the way. A cable's loose. Like, for example, I had a client yesterday, or actually 2 days ago, she was having trouble with her local network. She couldn't get a certain thing connected up properly, and she had moved some stuff around. It turned out to be just a loose connector at the wall that was pulled out slightly, and I had to physically go there. I should have tried to walk her through all of that, and I probably didn't do as good enough a job of that, but fortunately she was only a few miles away. Like, you get a little bit lazy if you know somebody's a few miles away, but if somebody's a few hundred or a few thousand miles away, that's not an appropriate way to manage. Okay, so do you understand that with layer 3 switches, we can create, essentially, it looks like a physical partitioning of networking, but it's a logical partitioning at layer 2. It's a layer 3 switch, but it's happening also at layer 2, because layer 3 switches, of course, speak at physical layer 1 and data link layer and network layer. So we're trying to prioritize traffic, keep broadcast traffic from bleeding into these different networks, so that these computers, these workstations, 1, 2, 4, and 7, if computer or node 1, or maybe it's a server, is broadcasting information, it's only going to go to ports 2, ports 4, and ports 7. Whatever's connected to them, we don't care. The second really good reason why to use VLAN capability is for traffic prioritization, and that is where the term VLAN tagging comes into play, and that's why I think I mentioned VLAN tagging in the last record in the last class session. In fact, I'm certain that I did. So in order for why we use VLAN tagging for traffic prioritization also goes hand in hand with multi-switch VLANs. The original VLAN capability only assumed that you had one switch in place. But let's say you have more ports or more nodes that you need to add to the same VLAN. If you don't have any more ports on this switch, if this was, let's say, a 48 port switch, and you've got 60 nodes that you need to logically partition into a virtual LAN at layer 2 and layer 3, you have to have some way for these switches to talk to each other. So I could take another switch. If I had more than 8 computers in this example, I could take another layer 3 8-port switch, put it underneath here, and I'll show you a better graphic of this in a minute. Here, let me just go ahead and show you that better graphic. In the case of a multi-switch VLAN. That's not it. There. Here's a case of a multi-switched VLAN. All 3 of these are 3 separate switches. They all have to be layer 3 capable switches. Now, they don't have to be the same brand, although it's usually a good idea, but because we have standardized VLAN protocols, 802.1q, for example, that is a standardized VLAN protocol which different manufacturers can program to, and it's happening, the VLAN part of this is happening in the actually in the data link layer. This 802.1q special field right here, this special 2 bytes right here, this is what's determining which VLAN a particular port or a particular piece of traffic belongs to. So this is better for a couple reasons. One, because we can have multiple switches all sharing the physical job of connecting all these devices together, simply because we don't have enough physical ports to handle the 70 or 100 different nodes that we want to connect together. So all 3 of these, and they're not necessarily connect in this in a ring like this. Sometimes they are, but it's not necessary to connect them in a ring. The reason we like to connect them in a ring like this is so that there's not more than there's still not more than 2 hops from any of these devices. So if this node up here in the upper left-hand corner needs to talk to this node in the lower right-hand corner, the traffic can hit this switch, that it has to hit that switch that they're physically connected to, and it can either take this path or this path, and then that path again to get to it. But we want to try to eliminate as many hops. And when I say that term hop, I'm talking about a physical connection point where your data link traffic is recreated. Data link frames, keep this in mind because several people kind of missed this or didn't understand this on the test. A data link frame is unique just to whoever's physically connected in a network. So if these were layer 2 switches, there is a data link frame between this device and this device, and that's a certain frame, and then a new frame is created and sent from this device to this device. So it's kind of like getting in and taking your data out of one car and putting it in another car to drive it to this other device. So there's some translations going on. The data is not modified. Your actual user data is not modified. It's just getting in a different car. The driver's getting out of one car, getting into another car. So we like to have as many or as few physical hops as we can, just because we don't want to have to recreate, either if it was a hub, physically recreate a signal, or if it's a layer 2 switch, physically recreate a frame, or a layer 3 switch, physically create a packet. But it would be okay if this link wasn't there for whatever reason, or this link wasn't there. And sometimes you do want to do that because each one of these blue lines, when we're drawing these things on draw.io and network maps, you've got to understand each one of these blue lines here. This is taking up one physical port on this device. So in this example, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 ports being taken up. If there's only 8 ports on this device, I cannot connect a 9th cable to this device. So sometimes you don't have the luxury of having multiple roads from one switch to another. But anyway, this is called, what we call this right here, this is a VLAN cluster of layer 3 switches. Each device gets its own IP address because it's layer 3, not necessarily to transfer packets at layer 3, although sometimes we do that. It is primarily so that we can talk to each one of the switches. We actually log into the switch. These layer 3 switches usually have their own GUI front ends, not always GUI, but in other words, they're running a web server that you can log into and manage. Not always. In fact, in a large environment, if there was 50 of these, all talking in a huge cluster like we have at University of Houston, we would not want to have to log into all 50 devices and say, okay, port 1 on here is part of this switch, and VLAN, and port 3 over here is part of this VLAN. When you are in a larger enterprise environment, we spend even more money and we buy layer 3 switches or managed switches, which can be managed by an external piece of software, a controller that runs. It might run on a node, it might run on one of these switches, but it can take all the changes and all the configurations that you decide to store on one, and it can propagate those out to all of the other layer 3 switches in that cluster. Much, much better for management. Those are called managed clusters, or mesh-based clusters, or mesh-based networking. Okay, so in this simple example here, we do have things partitioned by IP address ranges. We've got 3 separate Class C networks here. And like I said before, we don't have to do it at IP layer, but the reason that we do like to do it at the IP layer is because many times we want to not just arbitrarily block broadcast traffic, but maybe we want this LAN over here, this VLAN 10, not to be able to see, or this unit over here. Maybe we don't want the people on VLAN 10 to see web pages or be able to access servers on VLAN 20 or VLAN 30. And the way we can control logically is at the IP layer. We can't really control logically easy at the data link layer, not very easily. Network managers will typically log into layer 3 switches and employ firewall filters and firewall rules, which are done at layer 3 with IP address. So you sometimes have to bring it up into the IP layer so that you can say, if I've got some traffic from this one Class C 179.58.7.anything /24, and he wants to talk to 179.58.10.anything, regardless of wherever it is on this network, I can either permit or deny that traffic or drop that traffic. Permit it from certain IPs to certain IPs, permit only certain ports at layer 4. A lot of them actually allow me to control my networking at layer 4. So VLANs can exist at layer 3, 4, and 5. Or actually at every layer. You can have a port-based VLAN, a physical VLAN, where it's just ports like this. That's a layer 1 VLAN. Although I'm using a layer 3 switch to program it. A layer 2 VLAN is doing it by MAC address. Layer 3 VLAN is where we're doing it based on IP address for purposes of filtering traffic. Which when you start doing, and I know I haven't talked about the Wireshark yet, but we start talking about Wireshark, and I'm going to actually have you guys install more than just Wireshark on your computer. I'm going to have you install, or perhaps use, if you've got a PC-based system, use the existing Windows firewall that's built in, although it's a really crappy firewall, I would prefer, and it's also very different in terms of function to the Mac firewall. So what I typically recommend that students and end users do is turn off the Windows firewall, turn off the Mac firewall. These are the firewalls that protect your individual computer, your individual node, and download a standardized firewall application that speaks to your network layer, and it's the same whether you're using it on a Mac or a PC. That's a better thing to do because it's standardized. So the VLAN tagging, the reason that we use the VLAN tagging is, let's say that this node here needed to belong to 2 different networks. This is a manager maybe, and he manages part of the finance and part of the, or he's a network manager. He needs to have access to all of the networks. You can actually, one way to do that would be have, if there was 3 different networks here, have 3 different network cards in this unit and have 3 different IP addresses on each one of these 3 ranges and connect all 3 of those network cards to this switch. That's how we used to have to do it, but that's not efficient to do that. It also takes up ports on this switch, and this node probably doesn't need that kind of throughput. It doesn't need 3 gigabits per second if it's trying to belong to all 3 of these networks, just for purposes of occasionally accessing data on a server over here and a server over here and a server or another node over here. So the VLAN tagging, the frames that come out of the device, the tagging can be changed based on the application that created the data. Now, the application, and you have to tell the application, and you have to tell your computer, and it's not always available on every computer. Some laptops, Ethernet cards don't have capability for VLAN tagging. But if they do, that is advertised to the upper layers. The Ethernet layer, or the layer 2 of your laptop or your desktop that you're using, advertises to the upper layers, hey, I have VLAN capability. And that goes all the way up to the application layer, and different applications can decide, we're going to put a special tag in here at the application layer, and when it filters down to the data link layer, it'll stick a certain port number, or I shouldn't say port number, a certain VLAN number on that frame. So I could specify that this traffic is for VLAN 10 or VLAN 20 or the engineering VLAN or the finance VLAN, or that this traffic is web traffic or email traffic, which means it doesn't need to have high priority, or it's video traffic or audio traffic and it needs to have a higher priority. Now, the priority is not defined by that arbitrary number that you choose. You decide. Typically, network managers decide, okay, anything that has a tag of the number 5, for example, let's give that a higher priority than everything that has a tag of number 10. And where you set that is you log into these devices, you log into your layer 3 switch, and you specifically assign priority. You say, and we usually do it based on the tag number. We say something with a lower tag number has a higher priority, but not always. You can set that, you can change that on most of them. You can log in and say everything with a tag of 4,000, because you've got 0 to 4,095, or 1 to 4,096, excuse me. You're not supposed to use VLAN 0. If you use VLAN 0, that's supposed to indicate that this frame is not on a VLAN. It's intended for everybody. It's a general frame. It's kind of like using the emergency lane on the freeway or the HOV lane on the freeway if it's VLAN 0. But if it's VLAN 1, 2, 3, 4, 5, I can prioritize those based on that tag. And it makes sense to do it in order. VLAN 1, that's high priority. VLAN 4000, that's low priority. Some network managers do it the other way, but it's about prioritization of the traffic for purposes of the data flow. We're trying to make the data flow better or smoother, or control the data, or throttle the data. Sometimes, like if we allowed, for example, if we allowed all of our users on our different LANs here to listen to music or watch video, or listen to audio, I should say, not necessarily music, but watch video, because there are reasons why I would want employees to watch videos, even videos on YouTube, because they're instructional, because they're helpful, because I've put classes on YouTube and published them and told my employees, we don't really have an internal server, just like I don't have an internal video server for the videos for this class. I publish them on YouTube because that's a easier place to put them. We'll rely on their application layer infrastructure. So I've got to allow some bandwidth for that. So I can carve out, or I can allow, if I have a gigabit network, for example, I might carve out and say 200 megabits of that gigabit network are allowed for video. If that threshold is reached, don't pass any more packets or frames per second than 200 megabits per second. That will leave me at least 800 megabits per second for all of the other traffic that needs to occur on that network. Okay, so prioritization, throttling, those terms go hand in hand. You can go Google those terms. There will be questions on the test. What is throttling data? What does it mean? And I think some of you probably already know that, or I think it makes sense that throttling, like you're literally, you ever heard that term? I'm going to throttle you because I'm going to kill you, or whatever. I'm going to hurt you bad. Strangling you. That's basically, if your mom says, I'm going to throttle you, that means she's going to strangle you because you did something bad. Or at least if you were raised in the South like me. Now, virtual LANs, VLANs, why do we do them? For the flexibility of the networking, so that we can better control our traffic, where it's flowing, how it's flowing. So we can set up VLANs in an automated fashion, so that depending on the time of day, and of course this is dependent on the OS of those layer 3 switches. They're not all of them can do this, but a lot of them, you can change the priority based on time of day, or time of the month, or time of the year. So that if you know, for example, at the end of the month, you know, a lot of people are downloading certain things or needing to upload certain things to a certain website, you can automatically alter the priority of a certain network, for example, or a certain type of traffic. Traffic prioritization, quality of service, that's another term that I do need to understand. That goes hand in hand with the tag information. You can set what's called a quality of service tag in the frame or in the packet that comes from the node and hits the switch. And there are certain predefined quality of service numbers. I know I mentioned earlier that the prioritization is primarily done in the switches themselves, primarily done in the central hub. And it doesn't matter what the nodes try to do. The nodes are identifying the traffic. But that's not 100% true. There are certain applications which generate certain quality of service markers, which I can look at, like whether it's a video packet or an audio packet. In the case of voice over IP. In the case of voice over IP, your phone, which is a node on the network, is not connected to your PC. It's connected in this network, and your phone is one of these things, okay? It looks like a PC to the switch. But if we weren't specifically plugging it into a VLAN switch, and we needed it to be, and we needed those frames to be tagged as VLAN frames, most voice over IP phones are already throwing out their specific quality of service excuse me, markers, which say this frame, this packet, this needs to be treated with high priority. Whatever you're doing at the time, you're passing some web traffic or some email traffic through you right now, hold off on that for a second. Deal with these voice frames first, because we don't want them to be choppy. Now, I've seen this before. Some networks, they throw phones and PCs and servers and whatever all onto a switch, and this is a layer 3 switch here, but this is not a layer 3 switch here. If this is not a layer 3 switch, that frame hits this layer 2 switch, those 2 bytes in that field, they just get ignored. That layer 2 frame doesn't know, that layer 2 switch doesn't know and doesn't care about that frame and its priority. It passes the frame, but in other words, everybody becomes equal at that point. There's no differentiation. So it is important when you set up VLAN networks or VLAN clusters like this, that if you're going to do layer 3 and you're going to use quality of service and you're going to use VLAN tagging, it has to be done end to end, all the way up to your router or your gateway that connects you to the outside world. Let's pretend this is our gateway router that connects us to the internet or to the WAN. It's got to be end to end, which usually means all the equipment in your network has to be layer 3, and you have to program it all properly. So the disadvantages of doing this with VLANs is it is complex. It takes more time. Now, I somewhat disagree with this where it says may increase management when VLAN memberships change. That's true if you as a network manager are having to log into switches and change things around, but I argue that the management decreases. So pay attention to this. I disagree with the book and the notes because it's more correct to say that the management, once you've got a VLAN cluster set up, once you've decided on the priorities, you've made sure that all of the devices at the node end are properly putting quality of service tags on all of the data coming out of them. Once that's set up properly, it's nothing to manage it. But it is more complex in the beginning. So in the beginning, it takes some time to manage it. Also, if I was a hacker or if I was a rogue employee and I wanted to, and I was smart enough, I could tag all of my packets coming out of my computer as being voice over IP or high priority packets, and then I would get priority with any of my traffic coming out of my computer. I could install one of these pieces of firewall software like I'm talking about, and I'll tag, if I know what the appropriate tag is, I can tag all my packets. These belong to VLAN 1, high priority VLAN. So yeah, you can cheat at the node layer. So occasionally we have to figure out how to get around that. But the point is that the disadvantages are setting up a VLAN is complex. It does cost more. VLAN capable switches and managed switches, especially ones that do VLAN tagging and allow remote management from a piece of software that you can install as an application on a PC or on a node, and then remotely log in and manage several devices. That is complex to set up. Costs money. Also, it does decrease your overall throughput on your network. It decreases the speed. So if this was a nice, fast 10 gigabit network, for example, and the average, what did I say on Ethernet? The average overhead let's just use 1 gigabit because that's the most common one. The average overhead for layer 2 is about 3%. In other words, if you have a maximum gigabit throughput network, you're really only going to get about 997 megabits per second total download speed once you hit your application layer. Like if you're running a Google speed test or whatever, and you're doing a speed test, if you're getting a download speed of like 900 and 950 megabits per second, you probably are on a gigabit network. There's a little bit of overhead. When you take it up to layer 3, there's even more overhead, 5 to 6%, or possibly more. It depends on how busy these layer 3 switches are, how many filters you've put in the switches. Some network managers have put hundreds of lines of filters into their switches where every single packet that hits one of these switches has to literally be bumped up against 100 different rules. Is this packet from here? Is it from here? Is it this TCP port number this? Has this guy been banned? There's 100 different rules for every single packet. So in other words, every packet has to answer 100 questions Yes, no, yes, yes, no, yes, I'm cool, I'm good. Here are my 100 IDs that let me through the door. That's obviously going to slow traffic down. So the disadvantages that really need to be here are it's complex, it costs more, and there is a trade-off in that your overall throughput of your traffic is slower. You don't use VLANs if all of these nodes were servers. I probably wouldn't want to employ VLANs, or I would want to put those servers physically closer together with layer 2 switches if those two servers were backing each other up, for example. There's no reason to insert a layer 3 switch between a server and its backup source, or the thing that it's dumping all of its hardware, all of its data backups onto. This is for multiple different users on a network that have different needs and different uses. Okay, hopefully you guys understand now what I'm getting at with respect to VLANs and what the disadvantages are, because there are disadvantages. In the best practice, in terms of architecture, switches have the best cost to performance ratio, and that's true. The performance is the best because it's at layer 2, it's the lowest overhead. Actually, layer 1, if you just had a hub, if you wanted to connect two computers together, two nodes together, back to back. In fact, you can do this with most Ethernet. If you have what's called an Ethernet crossover cable, which the wiring is a little bit different in the cable, you can literally connect one laptop to another laptop, as long as the cable's not too long, and transfer files back and forth with it with a crossover network cable. And that's the fastest possible way to send data from one computer to another over a network. Don't even involve a hub or a switch. The switch will slow you down. That's one of the reasons why Ethernet allows you to do that. Allows you to have a crossover cable. You can go Google for that, Ethernet crossover cable, and connect back to back. Now you can't have a very long cable because the power output of most Ethernet ports on most laptops is very, very low. Most organizations are using routing at the core layer. So in that example, where by the time your traffic reaches this layer here to get out onto the internet, I'm not passing around frames anymore. It's all IP traffic at this point, and that's because it's been filtered and looked at by this cluster of VLAN switches. And VLANs are becoming more widely used, especially for organizations needing the flexibility of not just moving people around and moving nodes around, but prioritizing the traffic, because we do so many different things with one computer, and we want to differentiate what kind of data is coming into and going out of that node. The technology, we're using gigabit Ethernet for the distribution, gigabit Ethernet or faster for the core layer. We're usually at the core layer, if it's a large enterprise, we're using 10 gigabit Ethernet, or we're going to fiber optic. Also, we're doing redundancy at that layer. So usually, if we take a look here in these different buildings, this is 3 different buildings here. Here's the access layer. Each one of these blue lines is actually going to a switch which feeds a particular LAN. There's usually only one physical connection from your LAN to the access layer, to the MDF in a closet in your room, but very often there is more than one connection at the distribution layer, and that's for a couple of reasons. So you have some redundancy, just in case this switch, not necessarily that this switch fails, it just gets overloaded. So if this switch is too busy, the frame or the packet, depending on whether it's at layer 2 or layer 3, can be transmitted to this secondary switch here. So this is an example of load balancing. This is a mesh network. So we see a partial mesh network at the at the distribution layer. Sometimes we see it at the core layer, but usually not, because it's a little bit too expensive. And also these connections are longer distances. These connections are coming out of the buildings. And they are two separate cable runs a lot of times. Like at U of H, every building at U of H has at least two separate physical cables coming out of it to the central core layer connection point, which is the PGH building in the middle of campus. And I'll show you in another class when we get to the security part, how I figured that out. A lot of this stuff for us is not public knowledge and public information with respect to how the university's network is laid out, but even the casual user of U of H's network can figure out a lot by using some tools on your laptops while you're at U of H. Figure out where the traffic is going based on the names of things. The names of switches, for example, when you do a trace route. Okay. This gets expensive when you do this too. And these switches typically, there's actually fewer ports on distribution layer switches. In this example, there may be only 4 ports or 8 ports. There might be 48 ports at an access layer or a LAN layer switch because it's talking to a bunch of workstations. These are higher speed ports. These switches have more processors and more memory in them because they're handling more traffic. That's pretty much it for chapter 8. Let me just talk about very quickly, improving backbone performance. This is the same thing as improving performance at the LAN level. How to improve backbone performance? There's only 3 places you can look. Look at the devices, look at the circuits, or look at the demand. We either have to change the devices out or upgrade the devices if the network service is slow, add more memory, add more processors, or add more devices if we're out of ports, for example. We've maxed out that 48 port switch, go get another 48 port switch and daisy chain them together and stick them side by side. Circuits, either increase the speed of the circuits if possible, but if you're maxed out there because you're using copper cabling and you can't do more than gigabit networking because the cabling is too long in a lot of buildings, 10 gigabit can't be strung very far. You have to add more circuits. Demand, we increase or decrease the demand in the very same way. We move static data closer to the end user. So in the case of a local area network here, if we had a lot of training videos, rather than having the users go out into the internet to find these training videos, store them on a local server or a cache server. Sometimes we call it a caching server, here internally in this internal network so that you're viewing a copy of it. Many enterprises, many companies use locally caching servers and they can work transparently. Once information is downloaded and it hits this switch and it feeds through a caching server first, it keeps a copy of that data, especially if it's data that gets accessed a lot. And so the next time or the next node that needs to access that same video, it first checks on the caching server first. Hey, do you have a copy of that video? Yes, I do. Here, I'll just serve it up right to you. Works the same way as the caching. You guys all know what caching is, by the way? Works the same way that local caching works in your web browser. Do you all know? Do you guys know how caching works? I don't think I have to talk about caching, where if you go try to look at a picture or look at something that your computer has already downloaded from the internet, it'll just pick up the local copy off the hard drive. Same concept as reducing demand on our computer. We can put into place between us and the internet a caching server, or sometimes we call it a proxy server. It checks the internet for us and downloads pictures. Implications for management cost and necessity of upgrading the backbone networks will grow as the demand on our local area networks increases, mostly because of the different kinds of applications we want to support on our local networks. VLAN backbones provide flexibility and are becoming increasingly popular and necessary. These days, nobody's installing backbone networks that don't have layer 3 switches and VLAN capability, because even if they don't use them initially, your VLAN, the great thing about VLAN switches and layer 3 switches is you don't have to use that capability. You can put them in place and not program, and then they'll just operate as layer 2 switches until you decide, hey, I need to segment my switching, segment my networking. And as with LANs, Ethernet is now the predominant protocol in backbone networks. We used to use different protocols in backbone networks, protocols that were possibly faster, but we don't anymore because Ethernet is easily understandable. We don't have to worry about data breaking down because of a protocol change between your computer and a switch, and then the next hop up to a router. It's not having to go to PPP or SDLC or some other, not SDLC. There is a, I can't remember the name of it. IBM had some different layer 2 and layer 3 protocols, which is working better. And actually, like I said before, the lower down we can do stuff, the faster things are happening. So if you have a WAN connection to the internet, a lot of companies are actually getting layer 2 connections, which I'll talk about in the WAN chapter now. So that's it for chapter 8. Give me a moment, I'll pull up chapter 9. Just log in real quick to my content. Wide area networks, or WAN, not always the internet. A lot of people think WAN always equals an internet connection, but it doesn't always equal an internet connection. In fact, for a lot of organizations that have multiple sites, multiple physical locations, they set up WANs or dedicated connections between those different sites that are in addition to internet connections. So wide area networks, or WANs. We're going to talk about different WAN service types. I'm going to skip over a little bit in this chapter only because packet switched service, for one, is kind of dead and not that popular anymore. We'll talk a little bit about it, but not much. Wide area network, first of all, the definition is a WAN runs long distances, not always a long distance, but it typically is defined as connecting different physical locations of an enterprise together. If an enterprise has an office in North Houston and South Houston, or Houston and Dallas, or Houston and Shanghai, we set up a WAN connection potentially between those two locations. Organizations rarely ever own their own WAN topology because it typically spans physical boundaries which they don't have access to, unless they're using wireless, where they literally have their own antennas and they have allowance to use those antennas. Most companies are using WAN technology that they are leasing from common carriers. That is a term that you need to know. A common carrier, that was basically the generic term for telephone company. Common carriers would be level 3, Tata, AT&T, Sprint, Verizon, the carrier networks. These are the ones that own the antenna, the big cellular, and they're not all cellular, by the way. These are the ones that own the satellites. These are the ones that own the physical cabling. We have some local ones in town here, like Phonoscope, or they're actually called PS Lightwave now. Comcast also provides which is the commercial version of Xfinity, they also provide WAN leased line connections. They're also called leased line connections within the city and from city to city as well, wherever they have services. Comcast isn't everywhere. Common services that are offered: dedicated circuit networks, packet switch networks, and then VPN or virtual private networks, which a lot of you are already familiar with. So let me talk about dedicated service networks first of all. Most dedicated circuit networks are using full duplex circuits from common carriers called leased lines or private lines. These are point-to-point links. Let's take an example of an office in Houston and an office in Dallas that want to connect each other together. If they don't have their own satellite, which very few companies do, and they want a guaranteed nailed up, we call it a nailed up, or a guaranteed connection of maybe like 1 megabit per second or 10 megabit per second between Houston and Dallas, they will call up a common carrier that has services in both cities and say, hey, we want to get a leased line or a nailed up or a private line connection between Houston and Dallas. How much are you going to charge us per month? It's kind of like, it's almost like, not really like buying a private freeway. It's almost like, let's pretend there's a freeway from Houston to Dallas with 1,000 lanes on it. And you as a company can rent for 3 or 5 years one of those lanes, and only you and only your company can use that freeway. So that guarantees that you have the throughput. If you pay for 1 megabit per second, you get 1 megabit per second. Nobody else is sharing. No other company is sharing your freeway, your highway, your road from Houston to Dallas. Some other terms I've heard, by the way, are dark fiber. In the case of Phonoscope and Comcast, they have fiber optic cabling, which is already in the ground or already on poles that is currently not being used. It's literally off. There's no equipment on it. If it happens to be running in an area where you have 2 offices in the Houston area, for example, then the dark fiber runs between those 2 areas, or there is some dark fiber that belongs to that same network. They can internally connect that cabling up, that fiber cabling up, and let you provide your own fiber signal on it. Dark fiber is the best thing to get because you can specify and select the speed. And that sometimes doesn't cost more, sometimes costs less, because dark fiber literally means that's fiber that that company either is responsible for or installed and nobody's using it. It's kind of like, well, we built a freeway from the West Park area, or we built a freeway from West Houston to downtown, and nobody's currently using it. Well, we'd like somebody to use it. You provide your own cars, you provide your own traffic lights and your own police officers, and you handle that freeway. We'll let you just simply rent the physical space to use that. So the carrier installs circuits that connect the locations together. Don't worry about what these devices are called. It's typically billed at a flat rate per month with unlimited use of that circuit. It's usually pretty expensive. If you were to get a connection between Houston and Dallas at 1 megabit, or excuse me, let's go with 1 gigabit. Gigabit network speeds from Houston to Dallas, it's going to cost you maybe $2,000 a month, or even just one location in Houston to another location in Houston. It's going to be $2,000 a month. There's 3 components to the connection. There's a local component or a local loop. Then there's the connection between the 2 cities, and then there's the local loop in the other city. Let's say we're connecting Houston to Dallas. You have a connection point between your location and the local point of presence for Comcast or Phonoscope or Level 3 or whoever you're using, and then it piggybacks onto their big network, and then that data hops off their big network back onto the local loop for the receiving office in Dallas. That's another component. So there's 3 pieces, 3 circuits. Sometimes the local circuits actually cost more than the long distance circuits. A lot of times these take weeks or even months to set up, especially if they're not already built out. If there is physically not any cabling coming to your building from the carrier's point of presence, maybe it's 1.5 miles away, and they need to get some cable to you, it's going to cost a lot of money, by the way. Comcast level 3, they'll charge you $50,000, $60,000, $70,000 to get cable to your building. Sometimes it costs that much because you're having to go over freeways, you're having to go underneath streets and downtowns. Very expensive. So it sometimes takes months to get done. It took me 9 months to get a cable downtown at a building in Houston. And we had to sign a long-term, we had to sign a 5-year contract to get a good price on it. Adding or removing lines or increasing or decreasing capacity may be difficult and time-consuming and expensive. So usually when we order these leased lines, we try to assume that we're going to max out that circuit in the next 2 to 3 years. So we always overbuy. So a common carrier network, we don't use modems and muxes anymore, so you can ignore those two terms. And it doesn't really look like 2 wires. It usually is just one physical wire. It's better to think about this as one physical wire. The common carrier network, that cloud thing, kind of looks like the internet, but rather than this local area network in this office connected to the internet and traffic passing at the IP layer, you are actually connecting your networks together at layer 2, at the data link layer. Wide area network connections, dedicated circuit connections, work at layer 2, not layer 3. Layer 2 is better. The lower down things are, the better or faster things can happen. Less control, but faster. So if we need to get data, let's say all our data lives on this LAN on servers here, and we need to get that data as fast as we can onto all of the other nodes on our network, we want to do it at layer 2, not layer 3. Potentially. It'll get there faster. Okay, so that's one major difference between WANs and just using the internet to connect one office to another office. Is when you're using the internet, first of all, it's a shared network, and secondly, it's happening at layer 3 or the IP layer. Okay. Now let's talk about different physical architectures or different physical topologies of WAN networks, because unlike a LAN network where star is the logical and usually the most common kind of LAN topology, sometimes it does not make sense to use a star network, or a star network is not the best topology. So let's talk about these 3 different topologies by using an example of a network or a company that has offices in these different cities around North America. I'm actually going to skip ring for a second. I'm going to start with star. Star topology, it's assuming based on this example that their headquarters or their servers for this entity are in Toronto, and that each one of these locations here, Vancouver, San Francisco, LA, Dallas, and Atlanta, and New York, are their remote offices or their satellite offices. And all of those blue lines are dedicated connections. Now, physically, they may be passing through 10 or 15 different physical pieces of equipment at layer 1. But as far as these 2 offices are concerned, any 2 offices are concerned, at layer 2, it's one hop. In other words, a frame generated on a piece of equipment here in Vancouver is going unmolested into the equipment at Toronto. One frame, one hop. Okay, so keep that in mind whenever you see a logical map drawn like this. As far as you're concerned, that's what it looks like. The carrier has a much different looking map that has a lot more connections on it. Star topology, most common WAN topology for several reasons. One, because it's the cheapest, it's the simplest, And also it usually naturally grows because most organizations start out in one physical location. And then they grow from there. They add more and more offices, but they almost always have some headquarters somewhere where they started in this example. So star topologies naturally grow. Advantages to a star topology are there's a single point of control here in Toronto. If I needed to temporarily halt the network, let's say we find a virus on the network or there's something really seriously wrong, I can flip one switch here and kill the whole network. Or I can control the network if I'm not trying to kill the network, if I'm trying to maintain security and ensure that the network is up all the time, I can make sure that this one, and maybe it's only one device attaching all of these wide area network circuits together, I can make sure that that's very well protected. It's got a battery backup on it. It's in an air-conditioned room. It's in a very secure room. One point of failure, one point of control. There's pros and cons to that. Putting all your eggs in one basket, there's pros and cons to that. It's the cheapest topology. There are only 2 hops at maximum between any of the locations on your WAN. So San Francisco can send messages to Vancouver, and it's going to go through one of your physical pieces of equipment and one physical piece of equipment in Vancouver. So at layer 2, if you were to send a frame, or if you were to ping an IP here in Vancouver from San Francisco, you would literally see only 2 physical hops, assuming there's not any other proxy servers or anything in the way. Now, that's not the best WAN topology. It's not the most secure WAN topology. So some companies opt for a ring topology for their WAN. This is becoming more and more popular, and the carriers themselves will suggest this. Even within a city, Phonoscope, for example, if you say to Phonoscope, I've got 10 convenience stores and I want to connect them all up to my headquarters, they will suggest that you set up a ring topology network, because a star topology, in this case, if something happens to the central site, even if it's temporary, 15-second power outage or whatever, you've killed your connection to all of the other cities. None of these locations can do anything if the central site goes down. In other words, it's dependent on the central site. Furthermore, if one link goes down, let's say the farmer Ted in Montana here cuts a cable, or a moose runs into an antenna or whatever, something happens, and you lose the physical connection from Vancouver to Toronto. Until that link is fixed, until that break, wherever it occurs, is found. And keep in mind, from Toronto to Vancouver, how many miles is that? That's probably like, what, 2,500 miles? The likelihood of something physically happening to that link in 2,500 miles is very high versus 25 miles or 2,500 feet if it's a LAN connection or a backbone network. It's not very likely something's going to physically alter your LAN or your backbone network if it's not very big. But a WAN connection, you got to worry about farmers, like I said, cutting cables, construction companies, and we're covering a huge amount of, a huge footprint here. Lots and lots of miles. So it's much more likely something's going to happen to the circuit. So it's harder to find the breaks when it does occur. And many times, especially if it's something, it's rural in the middle of far northeast Montana here or somewhere in Canada, it might take several hours or even several days to find where the breakdown occurred. So in other words, a star topology is not very robust to the loss of one of these WAN connections, which in this example, even the Toronto to New York, that's several hundred miles. Okay, so ring topology solves that. We connect every city to 2 other cities instead of just one. So if a link breaks here, and again, this is at layer 2, and your traffic, and there's 2 physical ports in each city, maybe even 2 physical devices, your traffic, if it can't go on this link because it's broken, it can send the traffic on this link. Now, if Vancouver needed to communicate with Toronto and that link's broken, yeah, it'll take a little longer for the data to get there because it's got to send it through all these other nodes, but eventually it will get there. Also, this costs a little bit more because if you count the blue lines, how many blue lines are in here? We got 1, 2, 3, 4, 5, 6 circuits for the 7 cities. Here we've got 1, 2, 3, 4, 5, 6, 7 circuits. Pretend each one of these blue lines is $2,000 a month. $2,000 times 6 costs less than $2,000 times 7 every month. That might be a budget issue for some companies. Or maybe it's $10,000 a month. It depends on how fast these links are. They can be very expensive. Minimum, you're going to pay a minimum of $500 to $800 a month to connect 2 locations together, even within the same city. Even at slow speeds, we're talking 10 megabit per second. Not gigabit, but 10 megs per second, 20 megs per second. Minimum $500 a month to connect one location to another location across Houston. So it's a budget consideration. Advantages to the ring topology here is that it's robust to any loss of any one circuit anywhere. So we have some redundancy. That's the point. The disadvantages are it may take a longer time. There may be a delay while this circuit that gets cut here in Canada gets fixed. Also, the equipment and the programming and the routing is more complex because now you have to have a device that can make choices and make decisions. Okay, well, that link is down. Let me send it out this link. It may need to be layer 3 managed equipment that can make intelligent choices about how to route the message. Now, what some organizations opt for is a partial or even what's called a full mesh design. Now, very few organizations do this thing at the top, where they literally connect every city to every other city. The only organizations that do this are common carriers themselves, where they are providing the freeways. They're providing the communications for several other companies. Most companies do not have this kind of network because that's $2,000 times, that's 42 blue lines there. Way too expensive. But if you do have a very important network that you cannot afford to have go down, even for a few minutes, like you're an Amazon.com or an eBay or Facebook, something like that, you may choose to have some redundancy in your busier cities, your larger cities that have more users in them, depending on what you're supporting. So Atlanta here, for example, they've decided Atlanta needs 4 connections to different cities. They must have a lot of customers or a lot of need in Atlanta. Whereas in case of New York, there's only 2 connections. So maybe there's not as much of a need for the redundancy in New York. There's only redundancy here. So most companies can't afford this, but if they need the redundancy of a mesh network, they go with a partial mesh. It's robust. Full mesh is robust to loss pretty much anywhere. You can lose multiple connections all over your network, and your users probably won't even notice because you're literally 1 hop away. Dallas is 1 hop from Vancouver, 1 hop from Toronto, 1 hop from New York. Data travels very quickly on a network like this. If you have a partial mesh, your users might notice a difference if they lose 1 connection. If you have a ring type network, you will notice if you lose 1 of those. And then, but it'll be slow. But if you have a star, if you lose 1 WAN connection, you will definitely notice because you won't pass any traffic and all your employees basically have to go home or find some alternative method to connect Vancouver to Toronto, not on your layer 2 leased line WAN connection. another thing that all three of these offer, and the reason that some companies opt for a leased line connection or leased line WANs is because it's ultimately the most secure thing. If it's layer 2, it doesn't matter what's on top of the layer 2. It could be IP version 4, IP version 6, Apple Talk, old IBM networking stuff. It could be anything. It's up to the company. And that layer 3 traffic, that IP traffic, is not shared with anybody else, doesn't go out into the internet. So you don't have to worry about filtering traffic or looking for viruses or things like, well, maybe you do it, that backup. Looking for external hackers getting into your information, because this is a closed network. All three of these are a closed network. What's missing from all three of these diagrams is a connection to the internet. These are not internet connections. It's not public, it is private. So some organizations operate this way almost exclusively, and all the traffic goes back to one main site, like to Toronto, for example, and that one main site has the internet connection for the entire wide area network, and then they can control all the traffic right there, and they don't have to worry about, did some hacker attack the Vancouver office, because the IP addresses are not public. The traffic's not public. Okay, we're doing okay still. We got 7:15, still doing pretty good. So dedicated circuit networks, the advantage is to ring, robust to loss of any one circuit. Disadvantage, you might have a long route if there's a temporary outage of one of those circuits. It's called latency, by the way, the time it takes for a frame or a piece of information to go from one node to another node on a network. Star, it's the simplest to manage, it's the most common, it's the cheapest. Messages still get there pretty quickly, only 1 or 2 hops away. And circuit failures only affect one site. So maybe affecting one site is okay. Doesn't affect the whole network unless the main site goes down. The disadvantages are it's susceptible to traffic problems because we can't move our traffic. And another good reason, by the way, to have a ring is maybe this circuit doesn't go down. Maybe it's just real busy. Maybe Toronto and Vancouver are passing a lot of traffic back and forth with each other. So if New York needs to send some messages to Vancouver and the frames get here, or the routers, they're all talking to each other, and the Toronto router just says to the New York router, hey, I'm really busy right now with Seattle, send your traffic some other way. The New York router will say, well, I'll route it down here through the Atlanta, Dallas, LA, San Francisco connection. So the circuits don't have to be down. They just have to be busy. It's just like when you get on a freeway. Freeway's still open. You know, they didn't close the freeway for some reason, but there's a traffic jam for whatever reason, or traffic's going really slow. So you decide, well, forget this. Instead of taking I-59 or I-69 into town, I'll get on 610 and I'll go over to 288 and I'll go up 288. That's how I'll get to U of H, for example. You're just you're rerouting traffic. And then a mesh network, the obvious advantages are there's literally only one hop everywhere. It's robust to circuit loss anywhere. You can have multiple circuit losses, but the disadvantage is, and the thing that precludes most companies from doing this, is it's unnecessarily expensive. We don't need to do it unless we are a common carrier or we are an Amazon.com or something where we really, really need that super heavy mesh, full mesh network. Okay, here's the different carrier services that are available. There's actually 3 or 4 different services that are available, but T carrier service was the first one that was commercially available in the United States. It's still available. You can order a T1 or a T3. I'll talk about that in a minute. SONET, or Sonnet, some people call it Sonnet, but it's SONET. Synchronous optical network is very popular. By the way, this implies that term optical. What does that imply? That it's fiber optic. It's not copper wiring. T-carrier service is typically carried on actual physical copper wires, by the way. T-carrier service, most common dedicated circuit service used in North America, even though it's been out for a long time, and SONET service has been around for a long time. Your ATM machines, your any convenience store that has that sells lottery tickets, most hospitals, most inspection stations, garages that inspect your cars, most of them are required to have a T1 or a fractional T1 for security purposes. They can't carry that data over the internet or over IP. They have to carry it over data link layer connections. Insurance companies with some hospitals, they have T1 or fractional T1 service. A fractional T1 is only 64 kilobits per second. A full T1 is 24. Keep this in mind. There are 24 channels in a T1. If you take 64 times 24, you get 1.544 megabits per second. We simply rounded off to 1.5. So T1 is 1.5 megabits per second. You actually get 2 lanes transmitting and receiving. So it's really 3 megabits per second up and down. It's full duplex. So it's 1.5 over 1.5. Kind of like your Xfinity connection might be 100 over 10. This is 1.5 over 1.5. Not very fast, but it's dedicated and it's guaranteed. You're going to get that 1.5, and the only traffic that affects that throughput is traffic that your company is generating internally on that network. There is a specification for T2, but nobody ever, AT&T, Sprint, Verizon, nobody ever implemented T2. We have T3, which is basically 28 T1s. If you take 1.544 and you multiply that by 28, you get about approximately, we rounded up to 45 megabits per second. So T3, 45 megabits per second. T4, nobody ever offered that. That was 275 megabits per second. In practice, the wiring in most cities, the copper wire, the pairs of wires that went from a central point of presence in a city to the different buildings in a city wasn't good enough to use to get 275 megabits per second. So the fastest T3 service you can usually buy is 45 megabits per second. This is on copper wire. Okay. Any questions so far? You guys are being nice and quiet. Is it because it's 7:30 in the evening, or am I going too slow? I can speed up if you want. SONET service, synchronous optical network service. It's not offered everywhere. It's only offered in some cities. And that's the thing about T-carrier service too. It's not offered everywhere either. If a carrier does not have a POP, or what's called a point of presence, in both cities that you need to connect to. If you need to connect your Houston office to your Dallas office, and Phonoscope, let's just choose a local carrier, has a point of presence here in Houston, but they do not have a point of presence in Dallas, they can't provide you that service. It's usually intra-carrier specific. So there's very few providers that can provide services, T-carrier services, at that big layer where you're going from Houston to Dallas, or maybe even a bigger layer, Houston to London, for example. Usually that's going to only be satellite carriers that can do that. They don't typically share traffic. Some carriers have inter-agreements, like AT&T and Comcast. They do have some inter-carrier agreements where they'll agree to pass off what's called Metro Ethernet traffic, which is another form of layer 2 traffic, but most of them don't. You have to have a point of presence, a POP. So SONET service available in a lot of areas in Houston, in the country. Yes, it's available in Houston. Yes, it's available in Dallas, San Antonio, most large cities in Houston, Texas. It's a standard. Again, it's layer 2. It's a combination of layer 1 and layer 2. It uses something that looks like Ethernet. T1 looks like Ethernet. They're using frames. They're not Ethernet, but they look like Ethernet. They're actually more efficient than Ethernet. T1 frames have about a 99% efficiency. Ethernet frames only have about a 97% efficiency. Same thing with SONET service. With SONET service, you order it by channel, just like you would order, let's say you order a freeway, you order the use of a toll road. You can rent 1 lane, 2 lanes, 3 lanes, 4 lanes, any amount of lanes that you want, unlike T-carrier service. That's because it's fiber optic. OC1, OC2, OC3, it basically doubles each time. So in OC1, the lowest level, keep this in mind because this will be a question on the test. The first level of service of optical carrier service, OC1, is 52 megabits per second. So the slowest speed of optical carrier service is faster than the fastest speed of T-carrier service. So when companies are looking, and that's why there's not a lot of T3 being sold anymore. The only reason a company bought T3 is because they're in an older part of the country where the infrastructure just hasn't upgraded. They haven't changed to fiber yet. Smaller towns in the country. OC1 is 51 megabits per second, or we round it up to 52. OC3, 3 times that. OC12, 12 times an OC1. OC192, some carriers offer all the way up to OC768. OC3072, that's the fastest I've seen. OC3072, that's usually only offered on satellite, where you're basically renting the entire satellite and the entire range of that satellite. Nobody's using OC3072 unless, again, you are AT&T providing your own network. Now, entities like Amazon.com, eBay, Shell, ConocoPhillips, the big oil companies, they are leasing OC192s or internet service co-location facilities. All these big facilities in Dallas where there's just racks and racks and racks of computers and they're providing internet services, they have OC192, OC384, OC768 feeding internet into their locations, especially if they have multiple locations. But it's very expensive stuff. OC1, on the average, from point A to point B is going to cost you about $1,200 a month. Usually cheaper than a T3. A T1 will cost you about $800 to $1,000 a month. Almost regardless of distance, as long as it's within North America. If you want a dedicated service outside of North America, you usually have to go with a satellite type service or somebody that specializes in undersea cabling, such as Time Warner. Anybody ever heard of Time Warner? Time Warner Telecom, or TWT? Time Warner Telecom is what Roadrunner used to be a long time ago. Comcast bought out a lot of their local networking here in Houston. And what Time Warner Telecom specializes in, or Time Warner Telecom Pacific, I should say, is they run cabling along the bottom of the Pacific Ocean and the bottom of the Atlantic Ocean, and they connect cities together that way, from LA to Singapore, for example, or LA to Beijing, or Shenzhen, or wherever HPE and Foxconn and the oil companies and the other manufacturing companies have their plants in different parts of Southeast Asia. They're using OC services. Some of them are actually using, there's a couple of others. I'm going to skip pad networking. Nobody's really using that. I'm going to skip that too. I'll get to those other data link layer protocols in a minute. These are data link layer protocols. T1, T3, OC service, data link layer. We're not even talking IP. We're talking layer 2. On dedicated circuit, you have what's called a committed information rate and a maximum allowable rate. You may choose to purchase what's called a burstable or a fractional service, where they give you a certain minimum rate. You pay for 128 megabits per second, but you can burst up to gigabit per second as long as you don't burst up to that speed more than, say, 5% of the time. So these two terms you do need to know because they're associated with dedicated circuit services, committed information rate, maximum allowable rate. Sometimes they're the same thing. If the CIR and the MAR are the same gigabit per second, you're allowed the maximum gigabit per second or 10 gigabit per second or whatever you're paying for that circuit. But some companies, some carriers offer a service where the committed information rate is lower, assuming that your traffic is not even, which most companies, your traffic's not even. It's got peaks and valleys. You've got some periods of low usage and some periods of high usage. So why should I pay for a 10 gigabit connection? Why should I pay for a 10-lane freeway when sometimes I'm only using one of those 10 lanes, but sometimes I need all 10 lanes. So some carriers, not all of them, provide a service where they charge you less for a service where the CIR is less, sometimes as much as 10 times less than the maximum allowable rate, or the burstable rate they call it. Now, the reason they do that is because their internal network, again, to you, the user, the end user at layer 2, it looks like you've got a dedicated freeway and a dedicated lane on that freeway, or dedicated 2 lanes on that freeway. But not because it's virtual, not really. Really what happens is that freeway is really in virtuality on top of another freeway that the internal carrier uses to transmit several other organizations' traffic on. So maybe you can think about it like a freeway, a multi-deck freeway. So you get 2 lanes on one level and another entity gets 2 or 3 lanes on another level higher up than you or lower down than you, but you don't see their traffic because they exist in a different plane. But as far as the carrier is concerned, that's all one freeway to them because it's all carried in one physical piece of equipment, one physical connection from Houston to Dallas or Dallas to Vancouver. Okay, so they benefit, the carrier can benefit by basically aggregating your needs, spreading out your needs with some other company's needs, and they can offer you a lower rate, hopefully getting more customers. We'll skip that one. Okay, so there's some other layer 2 protocols. There's frame relay. That still exists, but it's pretty rare these days. There might be some old ATM machines and banks. By the way, banks cannot transmit their data across the internet. They must use layer 2 dedicated circuit services, either T-carrier service, SONET service, or Ethernet, good old Ethernet. It's not as efficient. And then there's another thing called MPLS, which is a newer layer 2 protocol, which is more efficient than Ethernet. And it doesn't really matter to you as an end user because all your traffic out of your computer becomes layer 3 anyway to go across that network. It doesn't stay layer 2 after it hits whatever switch you're connected to. Most companies internally for control purposes are running the layer 3 on top of their layer 2 dedicated network so that they control the traffic between different offices for VLAN purposes, for example. So it doesn't matter to you what the protocol is at layer 2 as an end user, even as a network manager if you're not managing the wide area connection. Most network managers do not manage the wide area network connection. The carrier does it for them. So there is frame relay that still exists. It's a legacy thing. Comcast and AT&T both offer Ethernet-based services. And the reason they offer the Ethernet services is if you are a network manager and you are managing your own networks at layer 2 between a Houston office and a Dallas office, if you're familiar with Ethernet, you might as well just keep using Ethernet from end to end. Ethernet end to end. The fewer protocol conversions that go on, the better. If an Ethernet frame has to be converted into MPLS, then back into Ethernet on the other side, again, there's some overhead. But if it goes from Ethernet, oh, that's weird. What did I press there? Never seen that layout before. If I go from Ethernet to another Ethernet frame to a third Ethernet frame, even though it's being converted, even though my driver's getting out of one car and getting into another car, he's getting into the same type of car. He's going from one VW Jetta to another VW Jetta to a third VW Jetta. Or one Lambo to another Lambo to another. He's getting in the same car. He's familiar with it, as opposed to going from a VW to a Mercedes to a Lamborghini. 3 different cars. There's overhead. Is that a good analogy? I don't know, maybe. I think it's a good analogy. How are we doing on time? We're doing great on time, I think. You guys can go look up on your own MPLS. I'm not going to ask you to know specifically what MPLS is. Just know that it's another data link protocol which is used specifically for wide area networks. So T-carrier service, frame relay, SONET service, MPLS are all used exclusively for WANs. You will never see it on a LAN. You will see Ethernet on a LAN and possibly a WAN. And Ethernet's usually what's on a backbone network, by the way. I'm not going to worry about it. Frame relay, Ethernet. Many carriers have switched or are switching to Ethernet for WANs. Again, it's a simpler topology to understand from point A to point Z. Keep in mind that this term, I mentioned common carrier earlier as being basically the generic name for a telephone company, which now telephone companies are not just telephone companies, they are communication companies. The telephone network, aka telephone numbers, 713-555-1212. That's what it is in our country. We refer to that as the PSTN, the publicly switched telephone network. That's an important term that you need to remember, especially if you are going to be managing converged network where there's voice over IP networking going on. The PSTN network is not going away anytime soon. If you had told me 20 years or maybe 30 years ago that we would still be using telephone numbers and telephone communication today, or if you had told me 30 years ago we would still be using fax machines today, I'd say you're crazy. There's not going to be fax machines. Well, guess what? Fax machines are still really, really popular. I don't know why. There are certain industries, the medical industry, the insurance industry, and the legal industry cannot seem to freaking get away from using fax machines. And the reason it pisses me off is because it's difficult to manage and maintain legacy applications for things that you could do in much better ways. Faxing is not the best way for, I mean, it's another way to do security, but it's not the greatest way to do security, because there's a lot of other ways we can do security these days. So it's called PSTN, telephone numbers, publicly switched telephone network. There's MPLS. Again, I'm not going to ask you to know what the physical specification of layer 2 is. Just understand that it is a layer 2 protocol, just like Ethernet is. Sometimes they call it layer 2.5 because it relies on some layer 3 items. Movements towards IP services. So telecommunication companies are moving towards all IP networks, and PSTN is being replaced. And I'm not talking about telephone numbers, because we're still going to have telephone numbers, but your telephone traffic, especially on your cell phones, is traveling probably at the IP layer, at layer 3, from one city to another, because again, when we bring the traffic up to layer 3, we can control it better. There's more overhead, and the IP traffic goes slower because of the overhead, but we can control it. We can control where telephone calls go and where they come from. We can hopefully do a better job of catching telephone spammers. We can't do it as easily at layer 2. So most telephone companies are doing their internal networking at the IP layer. Forget about the fact that you're probably at your company are also using IP because you're using voice over IP or VoIP. Make sure you know for exam 2 and exam 3 what VoIP stands for, voice over IP. Your phone, it's not a traditional phone anymore. It's a computer. It just looks like a phone. It's a computer, gets an IP address, speaks at layer 3 and layer 4 and 5 because it runs applications. And it's using SIP and RTP protocols, which are application layer protocols on top of IP, either IP layer 4 or IP layer 6. So VoIP is the concept, the general term for voice over IP, or replacing telephone audio and video conversations with a different method to transmit the data, whereas SIP and RTP are the application layer protocols. I'm typing this stuff into the chat window for those of you that wonder where I'm typing it rather than just WordPad. SIP and RTP. We'll talk more about those later. I know a lot about it. That's why I like to talk about it. Let's go ahead and stop here. We'll finish up chapter 9 tomorrow. I'll talk more about SIP and RTP. And VPN, we'll talk much more about VPN. I'll leave tomorrow to talk about VPN and why some companies opt to use VPN and not get wide area network connections, particularly for temporary or small network situations, or situations where it's one employee, or in y'all's case, one student that needs what appears to be, aka virtual, what appears to be a dedicated connection from your network to my network. So if there's not any more questions or any questions, I'll see you guys on Zoom tomorrow. Hopefully we won't have ridiculous storms like we did at noon today. And so check for your, excuse me, check the announcements, check your emails in case I need to postpone or have the Zoom meeting a little bit later in the day. And I'll keep grading the rest of the tests. I should have all of the tests graded and a curve or sliding scale number in there so that you'll see an exam 1 grade, an adjustment, and then an exam 1 adjusted grade. I'll try to get everybody's subnetting assignment also graded as well, but that's taken me a little bit longer. Draw.io, that's pretty easy to grade. Then I'll stick grades on, on that other stuff. Then I'll see you guys tomorrow. Let me stop sharing here. I hope I turn the recording back on. Yes, we're recording. All right then. Thanks for participating and coming in the evening time. I know for some of you that actually works better in the evening time. So go have some dinner and I'll see you guys tomorrow at 2. Some of you tomorrow at 2.